Hi, welcome to the part 3 of the assembly language primer for hackers. So in the last video, we had looked at the virtual address space randomization as well as prediction of the location of various segments for the 2.4 and 2.6 kernel. Now in this video, we will examine the registers, the stack, look at how to disassemble a C program and many other things using GDB. If you have not viewed the past two videos, would request you to use the link above and go view them first before continuing. Well, let's pick up our simple demo.c. This was the file which we used in the last video as well. And it's a very simple file. Once again, just a quick recapitulation, where we go ahead, take two command line parameters, can convert them into integers. Then we do a quick combination of gets and puts. And then we go ahead, call the add function, and then just print the sum of the two command line parameters. And we have the add function defined in the same file, which is a very simple addition function. So let's compile this. We get a warning, we can ignore it for the time being. Now, in order to understand more about this program through GDB, we need to load it within GDB. The way to do it is GDB and then simple demo. So this will also serve as a very simple GDB primer if you haven't used GDB before. If you have, probably some things might be a repetition. Okay. So the first thing, once the program is loaded, we can do is list the actual source file. That is done by the list command. 1 is actually the line number of the source file from where to begin listing. You can just press enter and we will be able to view the entire source file. Now to run the program through GDB, we use the run command, and then we need to give any command line parameters which the program expects. Now, if you remember, the program expects two command line parameters, which should be integers. So we can say run 10 and 20. Then the program has started running inside GDB. If you notice right now, we are of course at the gets and puts section. So let's actually enter something, demo, and then the same string should be echoed back and the sum should echo back as expected, and then GDB says the program exited normally, which is all fine and okay. So in this video, we'll try to explore various aspects of GDB which we will use in forthcoming videos in order to learn assembler. Now the first thing we can do with GDB is actually disassemble the program and dump the assembly language equivalent. Now the way to do that is to use the disassemble command and then give it the name of the function to disassemble as an example. So let's say we say main. Now once we do that, the assembler code for main is dumped, and don't worry if you do not understand much about what is being shown. We will get into all of this in later videos. So this is actually the various memory locations in the process, and this is the instruction which is there in that location, right? So we can enter and this can go forward. The interesting part which we can immediately see is that there are some functions which we recognize. So as an example, if we look here, then we notice that there is a call here to a to I, which is ASCII to integer, which is through the libc or C library which we've used. And again, there is a call to a to I. This is expected because we are converting both the command line arguments into integers. And then after that, we notice the gets call. Then we also notice the puts call. Then after that, interestingly, we notice a call to add, which is actually the function which is doing the addition. And then there is a call to the printf function, and then finally a call to the exit function, right? Similarly, we can disassemble the add function. Well, so this was about disassembling, and we'll get into how exactly we can interpret all of this in later videos. Okay, so now we've looked at how to disassemble the program. Now let's look at how to go ahead and step through the program instruction by instruction and actually see how the program is working. So in order to do that, let's first decide a place where we want to go ahead and halt the program execution. So one place where we can actually do that is probably, let's say, when things are about to be added here, right? Which is z is equal to x plus y. Now what we need to do, if you're familiar with basic programming, is set a breakpoint. The way you set a breakpoint is by using the break keyword along with, in this example, the line number in the program where you want to break. So if you notice, the breakpoint has been set for line number 8. Now there are many other ways using which you can set the breakpoint. If you want to learn more about it, just use the use the help command and just give the keyword. So it'll actually tell you what are the other ways using which you can set the breakpoint, so on and so forth. So use help wherever you want more alternatives or are confused what needs to be done, right? So we've set a breakpoint for line number 8. So now let's go ahead and run the program. Let's give it the command line inputs. Now it's actually at the get section. Let's give it something. Now if you notice, it did the puts, but then it went into the add function, and this is where it has hit the breakpoint. Now if you notice, GDB has already intelligently told us that the values of int x and int y are nothing but 10 and 20, which is what we pass through command line input, right? What we could have also done is we could go ahead and print these values by using the print command. Print x, print y. What one needs to understand is that while the print is going on, you need to be in the same context or stack frame while it's happening. Anyway, so now let's look at how the registers look like. So if you go back to our presentation, if you notice, we talked about all of these registers inside the CPU. How do we inspect them in GDB? The way to do it is use the info command and then info registers. Once you do that, a dump of all the registers, EAX, ECX, EDX, EBX, etc. are thrown onto SDD out. And if you notice, the important ones for us are ESP, which is the stack pointer, as we mentioned earlier, and the EIP, which is the instruction pointer. And if you notice, we are in add plus 13, right? This is the place where the next instruction is going to be executed. So this is how we can view the various registers, the flags, and the flags have been set. We'll get into exactly what these are in later videos. And then we have the various segment registers, the code segment, the stack segment, data segment, and others, right? So this is the way we can view the registers. And as we discussed in the presentation, we have general purpose registers, segment registers, instruction pointer, and control registers, right? And if you notice, apart from the control registers, which is actually internal to the CPU, everything else has been listed here. So now let's look at how to observe various values on the stack. Let's go back to the presentation, and if we notice, we said that the stack is nothing but a LIFO, which is last in first out, and it is arranged from high memory to low memory. So the question arises, exactly how does the stack look like programmatically? Now, what we need to do in order to view the stack. So this is the top of the stack. This is the memory location. So how do we view this? We do that using the examine command, which is the X command. So let's actually look more closely into exactly what this command is about by doing a help X. So it says examine memory and X, then you give the slash and then the format and then finally the address. So how is the format written? The first thing you do is give a repeat count, right? What does that mean? It is basically the number of units of memory you want to view. Now, exactly how is the unit defined? The unit is going to be defined by the size letter, which is given third in the order. And then exactly how do you want everything to be displayed is basically given by the format letters. So you can choose between hex, decimal, string, character, etc. So in this example, let's say we want to view this specific memory address, which is ESP, right? Let's actually go ahead and copy it. So what we need to do is we can say X and then say show me 10 units, display them in hex, and the units I need to use is basically bytes. So what this is going to do is, and then the memory location, starting at memory location, whatever we've given, it is going to display 10 bytes and show the output in hex, which is what the X denotes. So if you see now that it has gone ahead and shown us exactly how the memory location looks at this position. So what we can actually do is, generally what we are interested is in words, right? Because when you think about a stack at any given time, when you do a push operation or a pop operation, it generally happens over a word boundary, which is 4 bytes. So let's go ahead and put this in. So we'll get into exactly how a function, when it is called, the various parameters or inputs to the function are pushed onto the stack. So we'll cover that in a later video. However, what I want you to simply notice is the input. So let's actually quickly scroll back. If you notice, we ran this with inputs 10 and 20. Now, exactly what is 10? 10 in decimal means A in hex, and 20 in decimal means 14 in hex, right? If you were to now view the stack, right, you notice that this is nothing but the 10 which was passed on to the add function, and this is nothing but the 20 which was also passed on to the add function, right? And what we'll also see later on is that this 4 bytes is nothing but the return address. So I won't want to confuse you much here. Basically what we can do using the X command is view and examine memory. The stack is very interesting because whenever a function is called, all the inputs to the function are actually stored on the stack, and then while the function is executing, all the local variables are also stored onto the stack. And this is a very important part of the data structure, which is used time and again for exploitation and many other things. Okay, so now let's continue with our analysis. So right now, if you remember, we are still at a breakpoint where we are analyzing the registers, the memory, etc. If we now want to step one instruction at a time, we can use the S command. So if you notice, this was the next instruction, right? So we can keep stepping. And basically now the next instruction is going to be the actual printing. and then the final instruction is going to be the exit instruction. Program exited normally. The other way you can actually do this is basically when you hit a breakpoint, you can just press the C, which is for continue. And this will make sure that it will run till the end of the program. So what have we learned in this video? First of all, we've learned that if you want to disassemble any specific function, then you can just give the name of the function and you will get the assembly language equivalent. The other thing which you learned is how to set breakpoints, when you run a program, right? And then how to step through those breakpoints or how to continue and exit. Also, what you've learned is basically how to go ahead and look at registers while a program is running at a particular breakpoint. You also learned how to examine memory given any location such as the stack. And using just these very simple tools, in later videos we will look at how to go into in-depth assembly programming and as well as runtime analysis of various processes. So well, that's all for this video. Hope you enjoyed it. If you have any comments, positive or negative, constructive or destructive, please consider leaving a comment in the comment section below. This helps me get better and understand what the viewers want, and I will try my best to incorporate this in the next video. So in the next video, we will look at basic assembly language constructs. That's all for this video. Thank you.